You know, we spend a lot of time talking about the sheer scale of modern AI.
Oh, absolutely. The scale is the first thing everyone notices.
Right. We look at a model like GPT-3 with its 175 billion parameters, and we just marvel at it. It's this digital leviathan.
It really is a masterpiece of engineering,
Yeah, but there is a flip side to that scale that we rarely discuss.
which is that the bigger these models get, the harder they are to actually control.
Exactly. It's like we've built this massive, super intelligent ocean liner, but the steering wheel is, well, it's the size of a dinner plate and it's stuck in concrete.
That is a very good way to put it.
If I want that model to stop being a generalist and start being a specialist, say, I don't know, a legal expert or a medical coder or even just a pirate that speaks in SQL, how do I actually make that turn?
Well, historically, you didn't turn the ship. You just you built a completely new one.
Which brings us to the deep dive today. We are looking at a paper that I think is genuinely one of the most important pieces of computer science research from the last few years.
Without a doubt.
It's titled LoRA, Low-Rank Adaptation of Large Language Models, out of Microsoft. Edward Hu and his team basically looked at the crushing weight of fine-tuning these massive models and said, you know, there has to be a smarter way than just throwing more GPUs at the problem.
Right. And what they found isn't just an efficiency hack. I want to be really clear about this up front.
Okay.
This isn't just about saving money on your cloud bills, though, I mean, it definitely does do that. This paper actually reveals something fundamental about the physics, if you will, of how these massive neural networks actually learn.
And that's the hook for me, because it completely challenges the idea that to learn a new skill, you have to rewire the entire brain.
Exactly.
But let's not get ahead of ourselves here. Let's establish the baseline for everyone listening. Before LoRA, if you're a developer and you want to fine-tune GPT-3 to be a medical expert GPT, what is the standard procedure?
The standard procedure is what we call full fine-tuning, and it is an absolute logistical nightmare.
Break that down for us.
Sure. To understand why it's a nightmare, you have to look at the math. GPT-3 has 175 billion parameters.
Which are the weights in the matrices that define the model.
Correct. To fine-tune it, you have to initiate a training run where you are potentially updating every single one of those 175 billion numbers based on your new medical data.
So mechanically, you are calculating the gradients, the direction of error, for the entire massive model.
Yeah, and that is incredibly expensive memory-wise. You need to store the original model weights, the gradients for every single weight, and the optimizer states.
The optimizer states.
The variables used by the training algorithm, like Atom, to track momentum and things like that. The paper actually puts a hard number on this. To do full fine-tuning on GPT-3 175B, you need 1.2 terabytes of VRAM.
Wow. 1.2 terabytes of video RAM.
Yeah.
Let's put that in perspective for the listener. A top-of-the-line consumer GPU, something a hardcore gamer or a video editor might have, has maybe 24 gigabytes.
Right.
Even a massive enterprise card like an NVIDIA A100 tops out at 80 gigabytes.
So you aren't doing this on a workstation. You aren't even doing this on a single server rack. You literally need a supercomputer cluster just to load the model into memory and start the training process.
And that's just the training part. The deployment, actually putting the model out there for users, is arguably worse.
It really is. Let's say you succeed. You spend the millions of dollars, you run the cluster, and you create medical GPT-3. That new model is the exact same size as the original.
It's a 350 gigabyte file.
Exactly. Because you changed the weights, you didn't shrink them. Now imagine you have a business where you need a medical bot, a legal bot, a coding bot, and a creative writing bot.
I need 4 separate 350 gigabyte files.
You do. And you can't just swap them in and out of memory instantly because they are so huge. So practically you need dedicated, massive servers running continuously for every single specialization.
It's the definition of unscalable.
Totally unscalable.
It's like buying a completely new house every time you want to paint a room a different color. You just end up with a massive neighborhood of identical houses with slightly different living rooms.
That is a perfect analogy. And researchers realized this was unsustainable years ago. So before LoRA came along, there were a few major attempts to solve this efficiency puzzle.
Right. The paper spends some time dismantling these previous attempts. And honestly, I was a bit surprised by how hard they went on adapters.
Oh, they definitely tore into adapters.
Because on paper, adapters sound like a really solid engineering solution. You just insert a small layer between the big layers.
That's the theory. You freeze the giant, expensive model, and you sandwich in these tiny trainable layers, the adapters.
Yeah.
You only train the sandwich filling It saves a ton on training parameters.
But the Microsoft team points out a critical flaw that people were just overlooking: latency.
Precisely. The toll booth effect. You have to understand how modern hardware runs these models. GPUs love massive parallel operations. They want to do a billion things all at the exact same time. But adapters, by design, work sequentially. You have to process the main layer, then pass that data through the adapter layer, then back to the next main layer.
So you are basically introducing a bottleneck at every step.
You're breaking the parallelism. The paper mentions that on GPT-2 Medium, using adapters cause a noticeable lag in inference generation.
And if you are building a real-time application like a coding assistant where I need the code to appear right as I type, those milliseconds really matter.
Exactly. If the model feels sluggish, users just walk away. So adapters solve the training cost problem, but they ruin the user experience.
Okay, so adapters are too slow. What about the other big contender they mentioned, prefix tuning? That's where you just mess with the input prompt, right?
Basically, yeah. Instead of changing the model weights, you optimize a continuous vector that acts as a prefix to your prompt. It's almost like finding the perfect sequence of mathematical magic words to whisper to the model to get it to behave.
But the paper argues this isn't a free lunch either. It eats into the context window.
That's the major trade-off. Every model has a hard limit on how much text it can process at once, the context window. If your prefix tuning vector takes up 50 or 100 tokens worth of space, that is space you literally cannot use for your actual document or your conversation.
So if I'm trying to have the model summarize a really long legal document and my tuning takes up 10% of my space, I'm effectively making the model dumber by limiting what it can see.
Correct. Plus, the researchers note that optimizing these prefixes is notoriously unstable.
Yeah.
It's really hard to get consistent performance. You're navigating a very weird, rigid optimization landscape.
Okay, so let's recap the landscape here. We have full fine-tuning, which is impossibly expensive. We have adapters, which are way too slow. And we have prefix tuning, which eats up context and is unstable.
Which sets the stage perfectly for LoRA.
Enter LoRA.
Yes.
The core concept here relies on linear algebra, but I want to make sure we nail the intuition for you listening before we get into the math. LoRA stands for low-rank adaptation. We know adaptation means fine-tuning, but low rank is the absolute magic phrase here.
It really is. To understand it, let's look at what happens mathematically when a model learns anything. You have your original pre-trained weights, let's call that matrix W0.
Okay.
When you learn a new task, you are effectively adding a matrix of changes, let's call it delta W, to those original weights.
Simple enough. New weight equals old weight plus the change.
Right. Now, typically in full fine-tuning, that change matrix has the exact same dimensions as the original. If the original layer is a 12,000 by 12,000 grid of numbers, the change matrix is also 12,000 by 12,000.
Which is 144 million numbers just for one single layer.
Exactly. But the researchers had a hypothesis, and this is the brilliant part. They suspected that even though the model itself is extremely high-dimensional, the actual update necessary for a specific task is low-dimensional.
They call this the low intrinsic dimension.
Yes. Think of it this way. To teach GPT-3 to analyze sentiment in tweets, do you really need to rewire its entire understanding of quantum physics, logic, French history, and grammar?
Probably not. You just need to tweak how it processes positive and negative adjectives.
Exactly. The actual change required is very sparse. It lives in a much smaller mathematical space.
So the change matrix, this delta W we talked about, can be represented much simply.
Correct. And this is where the rank comes in. This is the matrix decomposition part.
Mm-hmm.
Instead of learning that massive 12,000 by 12,000 squared directly, LoRA represents that change as the product of two tiny matrices, matrix B and matrix A.
So instead of one giant square, you have two skinny rectangles that, when you multiply them together, create the square.
Two very skinny rectangles. If the dimension is 12,000, instead of 12,000 times 12,000, we define a rank, let's call it R. And we have matrix B, which is 12,000 by R, and matrix A, which is R by 12,000.
And the absolute shocker in this paper is just how small that rank R can be. When I was reading this, I was expecting maybe a rank of 100 or 500, but they're talking about single digits.
It is wild. They found that for many really complex tasks, a rank of 1 or 2 was completely sufficient.
A rank of 1. Wait, hold on. You're telling me that to turn a generalist model into a highly specialized expert, I essentially only need one vector of change?
Yes. That implies that the difference between general GPT-3 and SQL expert GPT-3 is mathematically incredibly simple.
That's fascinating.
It suggests that the optimization landscape is mostly flat. The model already has all the raw capability built inside it. It just needs a tiny, tiny nudge in a specific direction.
That is slightly mind-blowing, but let's look at the practical upshot of this. Because of this decomposition into these skinny rectangles, the number of trainable parameters must just drop off a cliff.
Oh, it plummets. For GPT-3 175B, using LoRA reduced the number of trainable parameters by a factor of 10,000.
10,000 times fewer things to track.
Yes, which brings us right back to the hardware problem. Remember that 1.2 terabytes of VRAM we needed for full fine-tuning.
The supercomputer cluster requirement?
Right. With LoRA, you can fine-tune GPT-3 on just 350 gigabytes.
Okay, to be fair, 350 gigabytes is still a lot. I certainly can't run that on my laptop.
No, you can't. But it moves the capability from only Google and Microsoft can do this, down to university labs, startups, and mid-sized companies can do this. And for smaller models, like GPT-2 or Roberta, you can literally now train them on a single consumer GPU.
But the storage win is the one that really changes the entire business model, right? We talked about those 350 gigabyte checkpoint files for every specialized model.
Exactly. With LoRA, you don't save the full model ever again. You freeze the base model. You only save those tiny A and B matrices. For GPT-3, a LoRA checkpoint can be as small as 35 megabytes.
35 megabytes. That's smaller than a high-res wood paper on my phone.
It is. So now imagine that deployment scenario we talked about earlier. You have one frozen base GPT-3 loaded into your server memory, the 350 gigabyte monster.
Right.
But you have these tiny 35 megabyte adapter files for legal, medical, coding, and poetry just sitting on your hard drive.
And because they're so small, I can load them into the model instantly.
Instantly. You can swap the entire personality of the model in milliseconds. It allows for a multi-tenant architecture where thousands of users are all querying the exact same base model, but each one has a totally different LoRa scan active.
It's basically the App Store model for LLMs. The base model is the iOS or the operating system, and the LoRa's are the tiny apps you download.
That is exactly what it is.
But wait a second. We talked about the toll booth latency problem with adapters earlier.
Yes.
LoRa is also injecting matrices into the model. Why doesn't LoRa slow things down the way adapters do?
This is the elegance of the linear algebra. We define the new weight as W equals W0 plus B times A. Because this entire operation is linear, you can actually perform the addition before you even start using the model.
You bake it in.
You bake it in. When you are ready to deploy, you multiply B and A to get your update matrix.
Yeah.
And you literally add those numbers to the original weights W0 in memory. You create a merged model.
So when the user actually sends a text request, the computer doesn't see original weight plus LoRa toll booth. It just sees new weight.
It looks exactly like the standard model structure. There's no extra layers. There are no loops, no toll booths.
Zero latency penalty.
Absolute zero.
That sounds almost too good to be true. I'm naturally skeptical of free lunches in computer science. Usually when you compress something by a factor of 10,000, you lose some fidelity. If I compress a photo that much, it looks like a potato.
Right.
Did they take a hit on accuracy?
That's the very first question I had when I read the abstract. They ran extensive benchmarks on Roberta, Daberta, GPT-2, and GPT-3. They looked at tasks like Wikischool, which is translating natural language to database queries, and Samsung, which is summarizing real conversations.
The results.
LoRa performed on par with, and in many cases actually better than, full fine-tuning.
Better? How could it possibly be better with 10,000 times fewer parameters? That feels completely counterintuitive.
It sounds wrong, doesn't it? But you have to think about overfitting. When you have 175 billion parameters to play with, it is incredibly easy for the model to just memorize the noise in your training data rather than learning the actual underlying task.
It's like a student who memorizes the exact answers to the practice test, but fails the real exam because they didn't learn the core concepts.
Exactly. By forcing the update to be low rank, by restricting R to 1, 2, or 4, you are heavily constraining the model. You are effectively telling it you cannot memorize everything. You only have enough capacity to learn the most essential fundamental patterns.
So it acts as a form of regularization.
Precisely. It forces generalization instead of memorization.
I want to dig into the experiments a bit more, specifically regarding data efficiency, because the paper mentions something called the low data regime.
Yes, this was a really fascinating experiment using the MNLI dataset. They wanted to test what happens when you only have a tiny amount of training data, let's say only 100 labeled examples per class.
Which is a very real-world scenario. Most companies don't have millions of beautifully labeled data points. They have an Excel sheet with maybe a few hundred rows.
Exactly. In this low data environment, the other methods really struggled. Prefix tuning in particular saw its performance just drop significantly. You couldn't figure out the right optimization path with so little signal to guide it.
But LoRa held up.
LoRa held up incredibly well. It outperformed the prefix methods by a very wide margin. It suggests that LoRa is extremely efficient at extracting the necessary adaptation signal even from sparse, limited data.
Because it doesn't need a mountain of examples to find that low-rank direction.
Exactly.
Let's get under the hood for a minute here. A transformer model has a lot of moving parts. You've got the attention mechanism, you've got the feed-forward networks. Where exactly are they putting these LoRa matrices?
The researchers did a huge ablation study on this, basically testing every possible combination to see what worked best. In the attention mechanism, you have 4 main weight matrices: query, key, value, and output.
The 4 horsemen of attention. Did they just adapt all of them equally?
No, they tried adapting just one, adapting all 4, and varying the rank budget. The most interesting finding was that adapting both the query and the value yielded the absolute best results.
Better than just putting all your parameter budget into one of them, say putting a rank of 8 on just the query.
Yes. They found that even with a lower rank, say, rank 4 applied to both the query and the value matrices, it worked much better than a rank of 8 applied to just the query alone.
Why do we think that is? What's so special about the combination of query and value?
If you think about how attention works conceptually, the query determines what the model looks for in the text. The value determines what actual information is retrieved once it finds it.
Right.
It suggests that to adapt a model effectively to a totally new task, you really need to tweak both the search mechanism and the content retrieval mechanism together. If you only change one, you bottleneck the adaptation process.
That's a great nuance. It's not just a matter of add parameters anywhere. Location really matters.
Location absolutely matters. And speaking of what it actually learns, there was a correlation analysis in the paper that I found profound. It explains exactly why this whole thing works.
This is where they compared the LoRa update matrix to the original pre-trained weights, right?
Right. They wanted to answer a specific question. Is LoRa just amplifying the features the model already thinks are the most important? Is it just taking the loud neurons and making them louder?
And the answer was no.
It's doing the exact opposite. They found the update directions had a very low correlation with the top singular directions of the original model.
Okay, decode that for me and the listener.
It means LoRa isn't just taking the model's strongest existing habits and reinforcing them. It's finding features that the model already has, but usually ignores features that are technically present but quiet, and it amplifies those specific quiet features.
So it's not teaching the model to see new things, it's directing the model's gaze to something it already knew but was previously completely overlooking.
Exactly. The pre-training gives the model a vast, comprehensive encyclopedia of potential features. LoRa just goes in, highlights the specific minor features that are relevant to your exact task, and shouts them out loud.
That explains why the rank can be so low. The capability is already there, it just needs a spotlight.
Precisely. It's an activation mechanism, really.
This brings us back to that philosophical point we touched on earlier in the deep dive, and I really want you to sit with this for a second.
Sure.
If we can radically change the fundamental behavior of a 175 billion parameter model by just tweaking a rank 1 or rank 2 matrix, what does that actually say about the model itself?
It forces us to completely rethink what these models are. We build them as these massive, dense, impenetrable blocks of numbers. But the actual functional manifold, the shape of the intelligence inside, seems to be much, much lower dimensional.
It makes me think of an empty cathedral.
That's a haunting image, but very accurate.
Well, think about it. We build this massive structure, 175 billion pillars, but the actual activity, the actual intelligence for any given specific task is just a tiny whisper echoing through one small corner of the room.
It absolutely raises the question, are we vastly over-parameterizing these foundation models? Are they mostly empty space?
Or, to take the more optimistic view, maybe they aren't empty. Maybe they're just incredibly full of potential.
That is the exciting angle.
Yeah.
If a rank 1 update creates a world-class SQL expert, maybe there are millions of other latent experts hiding in that exact same parameter space, just waiting for the right A and B matrices to unlock them.
It changes the entire ecosystem from big AI to agile AI, and we are already seeing this happen out in the real world. The open source community has completely run with this.
Absolutely. Because LoRa makes training possible on consumer hardware, you literally have people trading LoRA's online like they are trading cards.
Hmm.
Here's a LoRA for writing in the style of Shakespeare. Here's one for debugging Python. Here's one for creating Dungeon Master descriptions.
It democratizes the technology entirely. You don't need a $1 million grant to participate anymore. You just need a gaming PC and a really good idea.
It proves that you don't need to rebuild the brain to teach it a new language. You literally just need to rewire a few specific synapses.
We have covered the logistical nightmare of the 175 billion parameter beast, the failed attempts to tame it with adapters and toll booths, and the elegant, low-rank solution that Microsoft found. We've seen that it's faster, it's remarkably smaller, and thanks to that regularization effect, it's often actually smarter.
It is a very rare win-win-win in computer science. Usually, you are forced to trade speed for accuracy or size for performance. LoRA managed to optimize all of them simultaneously, simply by asking a fundamental question about the math of the update.
Well, on that note, we will wrap up this deep dive into LoRA. It's a dense paper, but the implications are massive for anyone touching AI.
Thanks for having me. It's been a great discussion.
And to everyone listening out there, next time you see a massive AI model doing something incredible, just remember, it might only be using a tiny fraction of its brain power to do it. The real question is, what is the rest of that massive space waiting for? Thanks for taking this deep dive with us.